Hi, everybody. Great to be here. It's been a fascinating series of conversations so far. This is going to be something slightly different from the conversations on content moderation. So I'm going to motivate the problem that led us to do this work, talk about the core parallel between programming languages and legal texts at the heart of it, walk through our formalization, show our implementation with a demonstration, and then talk about the broader lessons this has for formalizing parts of law. And I should say that this is joint work. We've been doing this for 5 years now with Shrutarsi Basu, who started out as a PhD student at Cornell and is starting at Middlebury as an assistant professor this fall. His PhD advisor, Nate Foster, Anshuman Mohan, who's now getting a PhD at Cornell, and Sean Parikh and Ryan Richardson, two very energetic and able undergrads. And we have one paper on this out onward 3 years ago. And we have a fourth, that's a very technical article on the programming language side of it. And we have a very shortly forthcoming law review article on it, which I'd be happy to share the draft of with anybody. It's near final, we're just getting the page numbering right. So here, let me motivate the problem to all of you with a pop quiz. To Sulu for life, then to Uhura and her heirs, but if she marries, to McCoy and his heirs. All of you who've been to law school, what interest does this create? What's the state of title? This is the kind of problem that first-year law students get in the unit on future interests in their property course. And if you have been to law school and you had a reasonably traditional property course and you remember all of this years later, you would know that Sulu has a life estate, Uhura has a vested remainder in fee simple, but it's subject to divestment because should she marry, then McCoy's shifting executory interest in fee simple will cut off her remainder in fee simple. And students learn these interests by drills. So this is the body of law that deals with how one piece of property, in particular real estate, these are where the doctrine's developed, can be divided among multiple owners over time. The essence of the previous interests was that instead of having one person who is the owner of this piece of property, instead Sulu owns it for most purposes and can use it during his lifetime, and after that Uhura will. But if this other event ever comes to pass, then McCoy will own it instead. And we describe those relations in terms of a set of legal categories that have developed over about 10 centuries. These are accumulated, accreted common law development, supplemented with time to time from legislation, and the system is extraordinarily formalistic. Lawyers are logicians who get to argue and change the answer if they're persuasive enough, but this is one of those things where there's extremely little room for argument within law. The rules are just bright, crystalline ones, and for that reason, they're actually quite frustrating to many law students. So there was a time, and it was about 100 years ago, if you took a first-year course in property in law school, you would probably spend 2 to 3 months learning all of these rules in exhaustive detail, reading dozens of cases on them. And today, they're not entirely gone from the course, but they're still present. And it's not uncommon to spend 2 weeks on this material doing lots of problems. And instead of having extensive discussions briefing the cases and the reasoning, there are lots of sample problems and students basically drill on them. And so for that reason, there are a whole bunch of student treatises just on this one topic. Here's the one I took that problem from. I've got a stack of these things at home, and many students basically have to buy this because it's so unlike anything else they do in law school that it's just really frustrating for them to learn. They feel like they didn't go to law school to do things like this. And professors have recognized for a while that this material is somehow different and problematic in a way that requires a defense. So James Kasner, one of the most prominent property teachers of the 20th century, author of one of the most widely used case books, basically tied learning this stuff to that it's a learned profession. And Would that supposition have to be revised if lawyers could no longer talk intelligently about fee tails after possibility of issue extinct, or distinguish a destructible contingent remainder from an executory interest in the nature of a shifting use? Other professors rejoined that, these seem to be like rules of nature, like laws of mathematics or physics, except for one crucial difference: the rules of future interests occasionally make no sense. So basically, this is a bunch of material that feels like it has landed in the law school curriculum from some other subject. And our inspirations, maybe that subject is programming languages. Maybe the system of future interests has the character that it does because generations of lawyers basically managed to turn it into a programming language without having either the concept or the theory to understand that that was what they had actually done. This is an area of law where, to an unusual degree, ambiguity and discretion have been wrung out of the system. Lawyers usually trade in reasoning by analogy and making distinctions, but here the rules are much harder-edged and much more bright-lined. And so it follows very consistent rules that certain kinds of language create certain kinds of legal relationships. So that if I use the phrase "to X for life" in the instrument giving somebody an interest in property, where X is that person's name, that creates the thing called a life estate. And that life estate has the characteristic that their interest will end as of their death. If I do some conveyancing, and I use some language Y, and then I stick on at the end, but if this event happens to X, then that creates an interest in X which will cut off the interests I just described in Y if that event ever happens. So these are very predictable elements, like the essential constructs of a programming language. They're modular because you can plug them in different ways. They are recursive because you could stack up to X for life, then to Y for life, then to Z for life, over and over. And they're generative because you can use them to make arrangements of surprising complexity and generality. And those are essential characteristics of a programming language. So our work is twofold. First, we formalized as much as we could of this language of conveyances. We call that Orlando, after Sir Orlando Bridgman, one of the great lawyers who drafted some of the most famous conveyances people read about in their textbooks. So we'll talk about its syntax and its semantics. We also simultaneously built an interpreter for that language. We call it Littleton, after the author of one of the most famous treatises on this system of laws. We did a camel for the back end, and then wired that up to a command line and web-based interfaces. So let me start with the formalization part in Orlando. There are essentially four moving parts to what we did. The first is a concrete syntax that models the actual language a lawyer would use or would traditionally have used in creating one of these interests that divides property among multiple people. Now, it is not going to capture every variation that they can use. We are not trying to do natural language processing to identify what different language they use and how to map all the varieties of wording onto one standard structure. Perhaps somebody could attempt that. I think it would be a very hard problem. Instead, we use the stylized language used to teach this to law students. This is not so much a model of what all lawyers actually do, as it is a model of the simplified, clean version taught to law students as the core of their intuition, on which they will then hang the broader understandings that they have of how to vary it and adapt it in practice. With that concrete syntax, we then have an abstract data type of the state of title, not tied to any particular language, just a way of saying this piece of property is divided among these people, and it will change possession under these events. So we do that with a tree structure, data structure that we call a title tree. The idea being that a title tree succinctly captures who owns what in this piece of property at one moment in time. We have a syntax-directed translation from the concrete syntax into the ADT, so that you can take one of these conveyances and effectively parse it into its parse tree, and then transform that tree into the title tree. The mapping is not quite one-to-one. There are a number of complexities, so a bunch of the legal intelligence here comes in saying, well, you can use all of these different variations in the language, but they will all wind you up with the same title tree at the end of it. And realizing we had to separate the two was, I think, the crucial breakthrough in our formalization. And finally, we have a semantics that updates the title tree over time based on events that happen. So if you have a title tree that says to A while they're alive and then to B after A's death, and you have the event A dies, it will update and simplify to simply B owns the property. And that's really the core of the formalization, is having a data structure that updates in response to external events. That way, a data structure plus a history of events can spit out the answer of what does the ownership look like at the end of that chain of events. And almost all of the actual legal doctrines of property law are in there. So, the conveyance syntax is a context-free grammar. And the basic units are, you have a conveyance where an owner, you then uses keywords conveys to, and then you have a series of one or more grants. The grant rule is itself recursive, so you can have a grant that splits into multiple grants. Here in the second line, you have one grant that becomes two interests, to Alice for life, and then an interest to Bob after that. And the recursivity lets you stack up any number of these in complex relationships. The grant can also turn into essentially the leaf node of a conveyance, which is a grant to a named person, to Alice, and the person's name is essentially a variable that you could fill in with any string, followed by a quantum, that is, how long will their interest last? That is a set of a number of keywords. For life is the keyword for creating an interest that lasts as long as they're alive. The full grammar that we describe in the forthcoming paper is more complicated, and we have an even more complicated version in beta version in the software that handles substantially more than this, but the core of it is essentially a CFG. And so with this, here is a derivation if you read from the top to the bottom, or a parse if you read from the bottom to the top. You start with a full conveyance. Owner conveys to Alice, and then to Bob and his heirs, and you just perform a parse on this to get yourself back up to the initial node in the grammar, the conveyance. And so armed with that tree, you have a structure for a particular conveyance. The second key moving part is the title tree, the data structure that represents who owns what. And this is given as another context-free grammar. T for a tree or title can be 2P, that is a grant held by one person. And if you just have the tree 2A by itself, that means that A has complete perpetual ownership of the property. It can also be the special bottom node, which corresponds to an interest that has completely terminated and is now nothing. It is an empty interest. All interests turn into that when they end. Finally, you have a set of orthogonal minimal elements to one person or to one set of grants, as long as the condition C is true. A branching statement that picks either T1 or T2, depending on whether C is true or false right now. And a simple sequencing construct, first T1, then T2. And we have a shorthand visualization of these. It's not strictly tree structured, but it's very useful for understanding intuitively how the parts fit together. So at the bottom, we have the interests that describe A owns this property while they're alive, and then it goes to B. So we've replaced the tree node for sequencing which is just a right-pointing arrow in the chart. And the way you read this is the leftmost box is the person who currently has the right to use the property. And in response to events, nodes on the leftmost branch of this tree will update. And those updates may cause certain branches to turn into bottoms that will fall off, and possession will move to the right through this tree. And as it does, the tree gets smaller and smaller until you wind up with eventually a single two-node by itself. We have, as I said, a syntax-directed translation from the parse trees to the title trees. I'm not going to go deeply into this because it involves a little bit of passing around of variables that's required to keep track of the fact that, for example, in some cases, how you describe an interest depends upon who gave it to you. And that dependence means that we have to push some variables through a bunch of these rules. Here's a simple example of what the translation looks like as you go. You start with the pair of two interests, to A for life, then to B and her heirs. And the and her heirs language is the standard legal language for creating a perpetual interest. So first, we split that into the two grants, and the then turns into a right arrow in our tree. We then transform the condition that for life in the concrete syntax into the while node while A is alive, where A is alive is the condition in the abstract data type. And then we do the same thing on the right. But instead of having a condition while B is alive, because that interest is perpetual, we simply replace the condition with true. There is nothing that can make that condition false, so there's nothing that can cut off B's interest. And at the bottom, we have the graphical representation of that, which is the same title tree I was showing you on the previous slide. Finally, we have a semantics for this. This is a style of operational semantics that are based upon Broskowski's derivative semantics, originally introduced for regular expressions. We found that derivative semantics worked very well for the incremental updating. The idea, in essence, is that at any given time, based upon the events that have happened up until now, some conditions in the tree are true and others are false. You simplify the tree by applying this delta function, delta for incremental update. And those rules cause certain interests to turn into bottom and then disappear from the tree. So the really important rules here are the while and the then. The while rules tell you that the subtree beneath a while terminates when one of two things is true. It terminates if the subtree itself is terminated. That's the third line in the definition. So if the T in that rule has become bottom, the whole thing becomes bottom. The other way it can terminate is if the condition C becomes false, in which case the whole thing becomes bottom. If, however, the subtree has continued, it is the subtree that updates under delta, so that the changes continue all along the leftmost branch. Then if you look down at the sequencing rule, this one basically comes out of the original derivative semantics for regular expressions. If the leftmost subtree has not terminated, it updates. But if after that update, the leftmost subtree has terminated, then we update the right subtree. And notice that in the first line, we apply delta only to T1 and not to T2. This is keeping with the idea that all of the action happens on the leftmost tree. So let me put this in a concrete example to make this style of semantics clearer. So here's a slightly more complicated one that shows off all the kinds of nodes. O gives A an interest for life, and then if B is married at that point, B also gets a life interest. And whether it's at the end of B's lifetime or because B was unmarried, C gets a perpetual interest at the end. And then we'll trace through what happens as B marries, and then A and then B die. So that concrete conveyance transforms into this tree. You have A's interest at the left, B's sits on the branch, and C's is at the end. So the first thing that happens is B marries. And this causes no concrete updates to the tree, because the only interest we're checking, the only condition we're checking, is the one on the leftmost branch, which is while A is alive, and since A is still alive, that condition is unchanged. The action starts at A's death. The first thing that happens is that the condition A is alive is now false, which causes the entire tree rooted at while A is alive to become bottom. So that's what happens, according to the while rule. But we're not done, because that bottom has to propagate through the rest of the tree. Since that interest is no longer entitled to possession, we have to find out what the next interest that is. So we go to, is B married? At that point, we can now evaluate the condition, is B married? And since B got married one event ago, the answer is yes. So that causes, of the two branches, the branch on which B is married, the yes branch, becomes the one that takes over. So now we have the simplified tree that while B is alive, B is entitled to possession, and after that to C. The next thing that changes title is when B dies. That replaces B's subtree with a bottom, which simplifies to just perpetual ownership in C. So that is the basics of the formalism. We implemented this using an OCaml backend because the fit between case matching and the strong type checking of an ML language with the parsing and rules for here turned out to be really clean. So there's about 3,000 lines of just framework and types. And then about 3,000 lines that actually have interesting legal content. There are roughly 1,000 that implement all of the rules in this book, everything from the doctrine of worthy or title to the destructibility of contingent remainders. There are about 1,000 lines that use some basic AI to reason about things like a person who is dead cannot marry after that fact. So you have to have some real-world knowledge to evaluate the conditions. And then finally, about 1,000 lines that implement the parser to translate different language into title trees. We have this supported against two front ends. There's a command line version that just takes as input a program and produces an S-tree representation of the title tree at the end. For more user convenience, sorry, an S-expression representation. For user convenience, we have an interactive web app. The front end is built in JavaScript, so we compile using JS of OCaml, the OCaml code to a very complicated JavaScript blob. It runs in your browser. The UI is done with Bootstrap, and it is available online. So to the online demonstration, we will now go. So there is Sir Thomas Littleton, our namesake, and we're going to try out a couple of conveyances. So here is what the same conveyance we've been looking at looks like in its interactive form. And you can see that it provides not just the skeletal version of while A is alive, then to B, but it does all of the interest naming that we had in the sample problems from the book. So we could put in a more complicated example. Let's do this one, and we'll hit the interpret button. And so now, to Lear for life gives Lear a possessory estate in life estate. Then if Goneril survives Regan, to Goneril for life, otherwise to Regan. So both Goneril and Regan have what we would have called contingent remainders in life estate, followed by a contingent remainder in Cordelia. Well, let's see what happens if we update the title in some way. So let's say that Regan dies. So Lear is still going to be alive, and now the interpreter has correctly reasoned that because it is certain that Goneril will survive Regan, the contingency on the vesting of her life estate has now been satisfied, and she now has a vested remainder. And this is in some sense pretty basic computer science, but this thing is now as smart as a law student has made it through first year property. these are the kinds of problems you would get on a final exam, and it can handle some pretty messy distinctions with aplomb. Like, people make fun of, oh, can it do shifting and springing executory interests? And I'm like, of course it can. Like we actually understand what they are now. Let me now return to the presentation and talk about what we learn from doing this exercise. So, formalizing these rules, I think, captures something that all of these treatises miss. And I mean, it's not their job to be elegant. And they've done their job very effectively. But there is something valuable in treating the system this way, over and above the fact that it actually captures the rules as law students learn them. The first thing is it recovers some of the underlying structure that learning all of these things out of rote handbooks has obscured. This was a living, breathing system at one time, and the judges who administered it had a sense of how all of these things worked and manipulated the concepts. And by being able to say something like, no, this is the actual definition of an executory interest, and it can arise in these ways because we have enumerated them logically, that actually recovers something closer to the way that the judges thought and makes the system more comprehensible. It also reveals patterns that are obscured underneath the proliferation of names and details. One thing we realized is that the system underneath here is actually pretty straightforward. What makes it messy is just the different rules that lawyers use to describe it. The terminology is actually more complicated than the underlying structure, and formalization brings that out. It also, I have to say, provides a foundation from which you can say, these rules do not make sense. The law students have been right for generations. We can point out with, I think, a greater degree of clarity the places in which this system is not making useful distinctions. So I'll give you some examples of insights we got from formalization. One of them is that if you just if you were a conveyance saying to A, the effects of that were different in 1300 and 1700, or in like 1900. Under the earlier rule, if you didn't say how long their interest was supposed to last, it was presumed to last for their lifetime. So we can model that with a rule saying that if you don't say how long it lasts, it's while they're alive. But the courts flipped that presumption over time. The rule changed so they presumed it was a fee simple, which lasted forever. So we treat, in the second set, the rule on an empty description of how long it lasts as being true forever. So you can actually model different legal rules by having different semantics. And in fact, in our interpreter, we have a dozen different toggles you can use to turn different doctrines on and off, or to toggle between their state, so you can see how different rules affect the reason. Other things, we discovered that some sources of ambiguity in interpreting conveyances are very familiar to computer scientists. So if I say, but if C marries to C, is that meant to cut off both A and B's interests, or just B's interest? Put another way, if C marries while A is still alive, should C take possession immediately, or does A retain possession for the rest of their life? This is a parsing ambiguity. Our grammar actually reflects the fact that there are two possible parse trees here, which have different interpretations. That's hidden if you don't have a formal way of thinking about it. And then finally, here's a case in which you can use 3 different kinds of language to create exactly the same legal relationships under 3 different names. The same exact title tree goes by 3 different names. It's a fee simple determinable, a fee simple with executory limitation, or a fee simple subject to executory limitation. Subject to is different than with a, for no valid reason. This is a case in which the naming complexity hides the underlying cleanness of what's actually happening. Once you have this formalization, it has great payoffs. One of them is this is a teaching tool that law professors who teach property, instead of going up there and lecturing about how the system works can actually have the students sitting and looking at it. They can see the diagrams and visually have a clear representation of what happens when. It also means you can experiment. You can say, well, what happens if A dies instead of B? Or somebody can ask, what if you phrased it that way? Well, just type it in and try it. We are working on our own version of this, in which every single example is an interactive, clickable widget. Just dive into it and play around to see what happens. So thinking more broadly, I think that this approach works because of the parallel between a programming language and the linguistic structure of what property lawyers have been doing. It works because property lawyers were using structured language to do things. So this fits with certain areas of law. I think it works for parts of property. I think it absolutely works for many kinds of contracts. It could be applicable in tax. This is not a universal model of all areas of law. This is not a replacement for all legal reasoning. It is just an idea that certain parts of law already have and behave like programming language in certain ways, and where they do, the tools of programming language theory enable us to make progress in understanding legal concepts. So that's what I've got, and I would be happy to have your questions and conversation.
Hi, thanks so much, James. I really enjoyed the talk. I have two questions. One sort of specific, and then one more general. The specific one is, I'd love it if you could go into more detail about, I don't know how to pronounce, like the GOF AI part of the code. Like you mentioned there was some minor AI that you needed to use to think about reasoning, and I'd love to hear more about that. And then second, I don't have a lot of experience with thinking about programming languages, but I'd love to hear what your, sort of what the most challenging aspects of this project have been, whether it was on the coding side or like in sort of trying to translate the legal theory to code. I'd love to hear more about that. Thanks.
So the good old-fashioned AI part of the work has been, I would say, more ad hoc than principled. We have a type of conditions, which is essentially a very, very restricted first-order logic. It has a couple of slots that you can put specific typed people or events into, and then it performs some very basic reasoning about what is true or false or ambiguous given the current state of affairs and a bunch of hand-coded ground truth rules, like people who are dead are unmarried. And it's not a general purpose theorem prover, it's just it reasons that this condition is true right now because I have these other things that tell me it's true. We are working on trying to extend that in a more principled and ambitious direction to capture the notion of things that are true and could become true in the future. We're going to probably use some kind of temporal logic, and then hopefully hook this up to a more industrial strength theorem prover so we can just encode our knowledge of the world as a set of axioms and then let it determine which things could be true if various other things happened. But that is a forthcoming research project, not something we've done yet. Your second question is about the biggest challenges. We spent a couple of years trying to get the right formalization of the semantics. We tried state machines, we tried a variety of graphs, we tried a bunch of different tree structures, and we finally worked out the 5 elements in this title tree data type that we were playing with after a couple of years of trying different things. And once we had that, and we cleanly separated the semantics of those from the concrete syntax that people use to create them, at that point, there was a lot of just working out the details. They were hard, and in some cases, figuring out what a given legal doctrine translates to was very tricky and controversial, but that gave us a foundation that we could hang everything else on.
Hi, Nathan Reidinger from University of Maryland. Great talk. I have a couple questions. One of them, I'm wondering if, and probably in your development phase, you encountered these types of problems, but what does a bug look like in your system, and what kind of consequences does having a bug, cause in terms of when we're imbuing these systems with potential legal consequences? What does that look like? And the second question is, had you considered what a system like this would look like for users? So, as lawyers, we're writing something for a client or we're interpreting something, but in some sense, it's possible when when a regular old person is saying, I would like this to happen, they might be able to use a tool like this and produce some kind of statement that would be interpretable and good for them, to be able to use later on in a testamentary type of way.
So aside from the crashing bugs that we get occasionally because the camel graph library doesn't work the way that it's documented, most of the bugs we get turn out to be results that I, with my legal training, know are wrong. That it just reports that B is entitled to possession when I know that that's not possible. Or it gives a name that I know conflicts with what's in the standard treatises. And so the bugs tend to be legally incorrect answers, and that's one of the many, many reasons that this thing is not a production system. Now, you can imagine the people who'd put more effort into it and dealt with something that's maybe a little bit closer to the front of legal practice would work on building systems that are pretty carefully done that way. I think for a long time these things are still to be used by people who can sanity check the answers. That said, you can imagine that this kind of framework would be amenable to drafting in the sense that you could take a state of title tree and run it in reverse to generate the concrete syntax that would generate that. And these people who are working on integrated smart contract and legal contract drafting are in fact trying to build interfaces like that in which you can work with some abstract representation of the legal state that it corresponds to that can then be reversed and turned into concrete language to achieve that result.
So there's two questions online, and I think I'll just read them because they're related to like when your system works and when it doesn't. So Boom asks, what other field of law do you think this programmatic thinking can be applied, maybe inheritance? And Peter says, as someone who just finished his property class in his first year JD, he found that it's very interesting. What parts of the conveyance system does your runtime not capture at this point?
So I'll start with the second one first. We have pretty much everything that comes in the future interests chapter and then the concurrent tenancies chapter. So we have future interests up through the rule against perpetuities. We have tenancy in common and joint tenancy. We have a little bit of different inheritance rules in intestacy and some very basic will doctrines. We are quite aware that it handles rule against perpetuity problems in an ad hoc manner. So it gets the standard examples right, but if you have something more complicated in which you could know that A or B has to happen and either way this person will be dead by then, it will not be able to do that branched reasoning correctly. And that's one of the main impetuses to have a more sophisticated AI system under the hood. In terms of where this is amenable to, it needs some place that has recurring rule-like structure for drafting. Will drafting is an obvious place to go, in part because it's closely tied to this system, and people creating trusts or other financial instruments could be doing something quite similar to this. It doesn't work for a more open-ended legal drafting. This is not a system for general statute drafting. It is really tied to, this approach is tied to the ownership of things.
Great. James, thank you so much for this. This is so interesting. I think you've hit on maybe the best area of law I could think of where something like this would be capable of being done. I'm curious to hear your thoughts about where we take this from here. It seems to me like a tool like this has maybe 3 different kind of suites of use cases. One's a very pedagogical, like to help 1L students learn the doctrines. We can use this as a way to visualize or present in a different structure these rules so that they can understand them. I see them in maybe a private live deployment, sort of while you're drafting these or while you're negotiating these, having this be a way that you say, see how this works when I'm negotiating if this was a contract instead of a deed. And then adjudication, where this could actually be used to adjudicate disputes, either as evidence of meaning or as the actual adjudication itself. And I'm curious to hear from you, where are you most excited in seeing a platform like this go in the medium term, I might say?
In the medium term, I am most excited about 1 and then 2. I think that this is a really useful modeling tool for building an intuition, and that it helps you take something, look at it, and convince yourself why it is the way that it is. That's a great educational place to have tools that work in this way. In the drafting setting, I think it's a great aid to people who are drafting systems to have modeling tools that they can use to work out consequences rather than having to hold as much in their head at the same time. I think that there's a huge amount of work to be done before these modeling tools are things you would actually directly use the output from. And I think they're not well suited, at least right now, to adjudication because it really is about extended engagement with the tool so that you track the concepts that it's using and are convinced that those are the ones that match the underlying reality. This is not a great system for somebody to jump into, type in a conveyance, and spit out the answer, because you will not have a good sense whether you have accurately captured the language people used, the contextual issues related to it. It is a first-pass modeling tool, not an oracle.
All right, I guess I'll take the last question. This was really fun to see for the first time an actual demonstration of law as code, which I've heard many times but never actually seen demonstrated. And this kind of picks up from the usability questions. I'm wondering, if you succeed with this and really get an effective programming language for describing these situations, is that going to help lawyers or make it harder for them? On the one hand, I feel like the extra precision should be really valuable. On the other hand, lawyers are on a different career path than computer programmers. And did they choose that because they do not think in programming terms? And if so, how can you provide them with the skills necessary to program their contracts instead of writing them?
So my career is dedicated to bringing lawyering and programming closer together. And so I think the answer is for lawyers who are looking at a tool like this, there's always been a subset, about 10 to 20% of people who go to law school who do think this way, and for whom something like this is the key to making it through what otherwise is incomprehensible. It actually provides the sense of elegance they're looking for to have clear rules. For the other 80 to 90%, maybe the way I put it is that this isn't so much asking them to program as making those rule-like parts of law more accessible to them by providing a bridge between the underlying concepts and the words that they're accustomed to using. And I think that's why the translation from words into diagrams is actually the most important part of what we've done on the implementation side. To say, not just that these are the rules and here's what will result, but to provide a visualization that provides a shorthand that's much easier to work with than the formalisms of the formalization of the language.
Great. Thank you, James.
Thank you all.